Okay, so now we can do the same for non-participants, and we will look a little bit later how it all fits together. But basically, you can solve. What I want to stress is that for Greenwood-Jovanovic model, you can solve analytically for the problem for participants and for people who never join the financial system. But you can never solve analytically for those people who actually make the transition. So that's where Greenwood-Jovanovic stopped, and they derived some properties of the policies. And oh, by the way, the sequence of individuals' decisions is called a policy. So, for example, if you, for example, saving rate is a policy. So, how much individuals save at each time period, how much he decide to dedicate to risky activities, it's called a policy. Okay, so Greenwood-Jovanovic were able to obtain the policy and value functions for participants and those who never joined, but they never were able to get the solution for those people who actually make the transition. And this is the most interesting case because that's actually what drives the growth. Because that's where the people make transition from being and basically subsistence level to become entrepreneur or whatever. So that's the most interesting case, and that's not addressed in Greenwood-Jovanovic paper, except for some very basic basic properties of this function. So what and why it's so difficult? It's difficult because, for example, if you, it's always looks like this, like this. So if you look at this expression here, you have kind of maximum of two different functions, and even each one of those functions are very smooth and very nice and has very nice analytical properties. When you get to the maximum of this function, especially with fixed cost, you get so-called even if you have like very smooth two functions, the maximum of those functions will look like this. It will look like very ugly. So if you try to find actually to solve this problem with using some whatever usual numerical method, you most likely will end up in some local minimum here, which would not give you optimal solution. So what Thousand Uyeda did, they used this famous Rob-Townsend method of lotteries to actually convexify this ugly function, and they showed that by choosing a lottery over portfolio allocation, you can smooth out all this non-concavity, and you can again get a very nice analytical, very nice function that you can actually optimize nicely. If you don't do that, I mean, the numerical procedure is not going to work very well. So that's the big contribution of Thousand Uyeda, that they finally found a method how to actually obtain the numerical algorithm to obtain this value function and obtain this saving and portfolio choice decision for the individuals. Okay, so now in this Thousand Uyeda model, we have a poor household outside the financial system, but eventually it accumulates wealth. It stays poor, but if it accumulates wealth, I mean, it's not a smooth process. You can accumulate wealth and then you can go poor again, but eventually you can accumulate wealth to a level greater than equal of certain critical capital level K star. So once you hit this capital level star, you will join financial system, and then you will stay there forever. Again, once you join financial system, there is no reason for you to drop out of the financial system. This is the feature of Greenwood-Jovanovic model, and we will stick with it for presentation. And here is numerical procedure. Again, just for the record, it uses Chebyshev collocation because the function is not discrete. It's a smooth function. It's a continuous function, so we don't really want to discretize it too much. We want to use approximation by continuous polynomials. And then we extrapolate it over the entire range of capital. Again, when the capital is very big, it's no different than the people who participate, and when it's very small, it's the same as people who never join the system. So again, I want to stress that if you use standard method to find a value function, if you use standard method of dynamic programming, this problem will probably never be solved, because this is not an equilibrium problem, this is growth model. economy grows unboundedly, it can grow to infinity, it can go down to zero. There is no natural bounds for the value function. So when you try to do optimization, it will most likely will not find you any value function if you just try to do standard approach here. But once you kind of bound this nasty value function by those two functions that we got actually analytically, then we are set, and then we can solve the dynamic programming problem. Okay, so there's more explanation how actually numeric procedure works. So basically, it involves maximization over the choice of saving and portfolio allocation for some integrals which can actually be taken analytically. So this maximization is done by simplex method for those who are interested. And then, but I want to stress that at each iteration, we actually do maximization over this mu and phi, and that's not what's actually usually done in dynamic programming. That's kind of different. And okay, and that's probably it for the math. And those who hate math can breathe freely now. And now we're going to the results. Those results are actually from our work for Mexico. I've just decided to save time and skip for the results for Thailand since they are very similar. So here we actually see the value function. This is the value function. I mean, value function is basically how good you are. I mean, this is the capital of wealth, and this is how good you are at different level of wealth. And people who are in financial system, they're always better than anyone else. And those people who are never joining, they're also kind of worse off than anyone else. So between those two are people who actually decide to join financial system in the future. Those people, this value function that actually 1000 and Ueda achieved. This is not the green one, Jovanovic. This is new from this work, and this is their value function. And this is additional value function. This one is to find this critical capital when those two value function interacts. This defines the value of capital that is required in this economy to actually join the system. So once you accumulated this capital, you are in, and then you kind of again eventually you go into the same value function as people who always were there. So this is kind of how it looks. And of course, for each of those functions, you have a sequence of individual decisions, saving decision, portfolio allocation decisions, and so on. So for each population, we can kind of we can model for the future what kind of wealth they will end up with, and how the economy in general will end up with. And here is, for example, of policy again for Mexico. This is our work. But this is basically the same. And so you see here that people who are in financial system, they save less. They don't need to save more because they're so well insured, so they actually save less. And people who are not in who never join, they actually forced to save more because they're not protected from bad shocks. They have to save more for the future. So this is basic. And people who decide to join in future, those red ones, first they have to save more, even more than people who never join. They have to save more because they decided to join. They have to save more. So they're saving money to join the club. And once they save, this part is actually it shouldn't be here. Once you join the club, it's about here. You go here and you don't save more again. So you can, this doesn't exist actually. You go directly here and then you go here.